In this video, we're going to discuss how we can find the basis for the column space of a matrix. I have my matrix A. It is a 4 by 6 matrix. I've row reduced it to the matrix B that appears here. The first thing is just to remember what the definition of the column space is. By definition, it is the span of the 6 columns of A, and that is a subspace of R4 in this case. So I have 1 through 6 columns, A1 through A6. And each one of those columns is a vector with 4 rows, so the linear combinations of them would live in R4, and the span would be the set of all those linear combinations, and therefore a subspace of R4. Similarly, the column space of the matrix B is the span of its 6 columns, and that's a subspace of R4, but it's important to realize that in general these don't have to agree with each other. And in this particular example, you can really see that if I take vectors that are linear combinations of these 6 vectors here, I'll never have a non-zero entry in the last row, where certainly that could occur for linear combinations of the columns of A. So you should expect that the column space of A is not equal to the column space of B in general. Certainly there can be situations where that is the case, but in general that shouldn't be expected. We will focus first on the column space of B because it's in row-reduced form, and the key observation here is that the non-pivot columns of B, so the columns that don't have pivots in them, are linear combinations of the columns that do have the pivots in them. And so to illustrate this, I see the first non-pivot column here is B2, and the fact that its only entry is -2 and the rest are 0 tells me I can take -2 times the first column, which is a pivot column. So I can write B2 in terms of B1. B2 is -2 times B1. I then look at the next pivot, non-pivot column. That's this one with the -6 and the 2. I have 2 non-zero entries, but they occur in spots where pivots occur in other columns. So -6 times the first one plus 2 times the second one should give me this fourth column. So B4 is -6 B1 plus 2 times B3. Then we go to this final column here. This is a non-pivot column, and it has non-zero entries in spots where I have pivots in other columns. It's going to be twice B1. I don't need any of the third pivot, but I need one of the fifth pivot here. And so what we're going to have is B6 is twice B1 plus 1 times B5. So what conclusion can we draw from this? Well, if the non-pivot columns are linear combinations of the pivot ones, I only need the pivot columns, which are B1, B3, and B5. They will span all of the column space because I get the remaining columns and any linear combination involving them in terms of the pivot columns. So the column space of my row-reduced matrix is the span of just the pivot columns. And more importantly, if I look at those 3 pivot columns, that is a linearly independent set, because if I take those 3 vectors and I form a matrix in them, I'll see a pivot in every column. And that's one of the equivalent conditions of being linearly independent. I'm specifically focusing on the pivot columns, and as such I will get linearly independent vectors. So they span and they are linearly independent, and that means this set of 3 vectors is a basis for the column space of B. And moreover, we can count the number of vectors in that basis. There are 3 in that set, so the dimension of the column space of B is 3. Now keep in mind, my question is find me a basis for the column space of A, not of B. But surely these should be connected in somehow. Even though they're not the same space, hopefully I can glean some information about the column space of A from the column space of B. And the answer is yes, just look at these relationships among the columns of B. I'm going to rewrite them in a homogeneous fashion here. So I'm taking each one of these equations, and I'm just pushing one term to the other side so that I have homogeneous equations equal to 0 on the right. So each one of these relationships among the columns of B is really just corresponding to a solution to the homogeneous matrix equation B times x is equal to 0. So for example, if I took x to be the vector whose first entry was 2, whose second entry was 1 and then 0 for the remaining 4 entries, that vector x would give me a linear combination that would look like this, and it would have to equal 0. So every solution x here is corresponding to some weights over here that get me 0 when I linearly combine those 6 vectors of B. But these matrices are row equivalent to one another, of row reduced. So the solutions to Bx equal to 0 are the same as the solutions to Ax equal to 0. And what that means is that any linear combination of the columns of B that get me 0 also will result in a linear combination of the columns of the matrix A that get me 0. And you can see some of them. It's not so easy to see it in A. It was easy here to see in B, but it looked like the second column was minus 2 times the first one. If you take the first column of A and you multiply it by minus 2, you should get every entry in the second column. If I double and negate the sign, I will get the second column there. And I would encourage you to just pause and take a moment here and see that the other relationships are held. So for example, if you take minus 6 times the first column of A plus 2 times the third column of A and add that together, you will get the fourth column of A. Hard to see up here when it's not row reduced, easy to see here, but these relationships among the columns of A are preserved as I do row reduction. What that means for me is that the column space of A is the span of the 3 pivot columns of A. I know which ones those are because I've row reduced. I can see that they are the first, the third, and the fifth one. So the first, the third, and the fifth column of A will span. Moreover, they are linearly independent because they have pivots in each of those columns. After I row reduce, I'll see those pivots. And therefore, those 3 vectors are a basis for the column space of A. And of course, the column space of A has the same dimension as the column space of B. It is a 3-dimensional subspace of R4. All right, well, here's our big conclusion, what we observed from this example. The pivot columns of a matrix A form a basis for the column space of the matrix. So if you want to find a basis for the column space of a matrix, you should row reduce to find the pivot columns and then go back to the original matrix. Those vectors, the pivot vectors in the original matrix, form a basis. There's an associated terminology that goes with this. The rank of a matrix A is the dimension of its column space. So the rank of A is the dimension of its column space, and we'll write that as Rnk of A is the dimension of the column space of A. So rank of A, Rnk. And ultimately, you can only have one pivot in any given column, and the dimension of the column space is the number of those pivot columns because the pivot columns form a basis. So if I want to find the rank of a matrix, I am essentially counting the number of pivots of a matrix. So the rank of A is the number of pivots. Recall that the dimension of the null space, in complement to that, is the number of non-pivot columns. If you're trying to solve the homogeneous equation, you care about how many free variables will be in your solution set, and that's going to be determined by the non-pivot columns. And so we get an easy little bit of arithmetic here that is called the rank theorem. Suppose A is an m by n matrix. In particular, it has n columns. Then the rank of that matrix, which is the dimension of the null space, which is the number of pivots, must be the number of columns, total number of columns, and then take away the dimension of the null space because that's the number of non-pivot columns. Every column in your matrix is either a pivot column or a non-pivot column, and essentially we're saying that if you take the rank, number of pivots, add that to the dimension of the null space, number of non-pivot columns, that should equal the total number of columns.